Hi, everyone, and I want to welcome you back to this fall semester. It's going to be a unique one for sure, not only here at Pacific, but basically around the world, actually, with kind of this remote teaching. But I want to welcome you to ENGR110, which is Instrumentation and Experimentation. This is a really unique and fun class where we're focused on learning how to determine uncertainty, how do we design experiments, how do we build apparatuses in order to kind of measure increasingly really small or quantities where we need precision is a must in order to kind of find some new frontier either in bioengineering, material science, mechanical engineering, really whatever field of engineering that you're in. So this is a really fun class. We cover a lot of a variety of topics. Unfortunately, this class also really heavily depends on kind of in-person, hands-on lab activities, but we're going to do our best in these uncertain times to kind of provide the best virtual hands-on lab experience that you can in order to kind of understand and determine some of these topics. But I'm excited to be here today. I'm excited to see everyone once we get into class, and I hope you enjoy these YouTube lecture sessions, and then I hope to see you again in our in-person lecture experience where we could work on these problems and kind of talk about this theory and actually apply it to some real-life problems. So with that being said, let's talk about what you're in store for this semester. So as I mentioned, this is ENGR110. And then just a quick disclaimer, I provide my lecture notes in LaTeX because my handwriting is bad, but hopefully we'll both deal with it. So, but yeah, all the LaTeX notes are provided to you. If you need help accessing that, please let me know. So in ENGR 110, the class is pretty much broken into three parts. So part 1, part 2, part 3. We're going to have basically 3 exams in this course. One of them will be held during our final exam week. It is not a cumulative exam. So part 1 will deal with lectures 1 to 5. Part 2, these lectures 6 and 7. Don't think that that's easier. It's actually these last 2. And then part 3 is lectures 8 to 9. The lectures are not the same in length. This lecture is extremely long, so get ready for that one. It's mechanics. My background is material science, so I can't help myself. I'm going to write a lot for that lecture. But anyways, this is how the lectures kind of break down in terms of covering these parts, and the exams will kind of cover these different topics. So the first part 1, is going to deal a lot with, and actually should hopefully be familiar to you if you took statistics in high school. If you still remember it at this point. Obviously, we're going to cover some more in-depth things that you probably didn't see, but initially it should be a little bit more straightforward. Hopefully, it's a lot of material that you've seen before. So we're going to deal with statistical analysis, so z-tables, t-tables. We're going to deal with uncertainty, error, chi distributions, and then the last part will be propagating error, which you probably have not seen before. Propagating error. But we'll deal with that when it comes. So part 1 of this class should hopefully be okay. It should be a little bit straightforward in terms of the, again, not too complex content, especially if you've taken any type of statistics course in high school or previously. So that's not too bad. So, but I want to warn you about one of the things people do in this course is they do really well in the first exam in part 1. They relax, but they don't know that in part 2, what's coming is Fourier analysis. So you hopefully have seen or maybe have come across Fourier analysis before, but we are going to deal with how to do CFT, continuous Fourier transforms, discrete Fourier transforms. We're going to deal with topics dealing with signal aliasing, also spectral leakage. Now, Fourier analysis, at least, let me misspell, but it doesn't matter. Spectral leakage. Fourier analysis, at least to me, you get hit with a lot of these fairly complex and laborious, actually, equations initially. So you can get easily lost inside of the math, but we do not want to do that. We want to kind of keep essentially we want to be able to keep our eyes on what is the application. How do we actually apply Fourier analysis to our lives as engineers? And actually, Fourier analysis can be applied really regardless of what type of engineer you are, bioengineer, mechanical engineer, material scientist, it doesn't matter. So it's actually really ubiquitous, really important to know this, but my warning was people usually do well in this part, they relax, they kind of miss out on kind of these details in the math component here, and then there's some real struggles that could potentially occur. So we don't want to do that. So we don't want to fall into this trap of how do we calculate, or falling into the trap of the math of calculating these harmonic coefficients. For example, a sub n equals 2 over your period t, integrate from 0 to t, the original function y of t times cosine of 2 pi n time t over period dt. A lot of math is involved in here. We want to, again, remember, how do we apply it? How do we actually apply this equation to our real life kind of scenario? So much more on that later, much more fun math. But again, we'll use one of the actually really interesting and fun parts of this course is that we're going to learn how to use some analytical tools, some coding tools for engineers that are going to allow us to kind of perform this math really straightforward and easily, so you don't have to kind of go back and remember your algebra or your calculus notes. You need to do that by hand anyways, but we'll do that much more faster and efficiently. So that would be my one concern. Again, we're not concerned, but just be aware of that this part 2 is much more difficult conceptually than this part 1. And then we get into kind of the really fun part. So again, I think this course is primarily for bioengineers, mechanical engineers, civil engineers. So that involves, I think everyone's really interested in kind of mechanics, specifically mechanics of materials. We're going to deal with strain gauges, a little bit of circuits, but not enough to scare you off, so don't worry too much about it. Again, these are conceptually more difficult topics, So in exam 3, we are going to be dealing really mechanics of materials, and then how do we apply these fundamental equation to these stress tensors. So if you've taken my ENGR145 course, you've definitely seen this before. How do we deal with this nasty looking tensor and then apply it to strain gauge applications? So 1, 3, 2, 3, 3. And how do we actually measure strain in a material? So much more on that later. So that's what we have to kind of look forward to in terms of the structure of this course. So let me erase a little bit here, and let's get actually a little bit more detail into what you might expect on an exam and some topics that are most likely going to come up. So just to focus you for the beginning of this semester to kind of see, and you go back to this video and kind of as you're trying to study for exams, you could focus in on a couple particular topics. So remember, everything's in play potentially. So all lecture notes, anything kind of recorded on a Zoom lecture video, but I am much more likely to ask, I'm here to test your knowledge, I'm not here to kind of trick you. So I want to see if you could kind of do the critical things that we need you to have, the knowledge you need to have as an engineer. So let's look for part 1. So for exam 1, again, that's the statistics component, determining uncertainty. So exam 1, all my exams have 4 problems. Now they might have lots of sub-problems, so you'll have 90 minutes to complete the exam, and you'll have 10 minutes to upload your solutions onto our Canvas site. So during the exam, open notes, open everything, use Mathematica. Please use Mathematica. I think it will be really helpful. Again, I'm most concerned about your approach to the problem. So partial credit is really heavily weighted in this course, but again, this course in particular, I am a little bit more concerned about the final number being quantitative, since some of the topics aren't super obtuse, and because you now have all these kind of open notes, open Mathematica, so I'm going to be a little bit more harsh in terms of the grading on that aspect. But again, make sure that you have the concepts down first, and then you use Mathematica in your tool. The one thing, obviously, you must take these exams independently, so no collaborating with your other classmates, no getting help from anyone outside. I'm not going to be installing any proctoring software. You're an adult, I'm an adult. We have some trust and understanding that you will not cheat, because I trust you. You know, there's an honor code here at Pacific. However, again, if I do find some instances of cheating, again, you will automatically fail a course, unfortunately, and then be subject to some disciplinary measures. But I trust you. This has never really been an issue. So let's get into what the exam is going to entail. So 4 questions for each exam. They're all equally weighted, so 25 points apiece. There's no really extra credit on this exam, but again, show your knowledge. That's the kind of key thing I want to emphasize a lot in this course. So for exam 1, what are going to be the possible questions that you might run into? So 4 questions. What can possibly be asked? Well, we deal a lot here with like hypothesis testing. Actually, the last question will almost definitely be propagating error. Propagating error. So this deals with precision and bias error. Again, this will become more clear when you watch this video back. It'll help you kind of study. So that will almost always be that last problem. So you already know what one problem is going to be, or at least in general, what topic it might cover. Chi-squared problems are very attractive. So they cover kind of multiple topics. I could throw in here inside this chi-squared question a z distribution or even a t-table distribution problem, but most likely I could throw in a z-table question hidden in here. So chi-squared problems are really attractive for me to kind of ask because I could ask multiple different things in there. So chi-squared is really important, and we'll see that again once we do our exam review. So remember, don't be too worried about the exams. Study as best as you can. To focus. If I was a student in this course, I would really focus on the practice exam. I would come to our basically 4-hour review session. Hopefully, it won't take the 4 hours, but I'll be there for the 4 hours, and we'll go through problems. We'll see how we want to go about solving it and take it apart piece by piece. So it shouldn't be too overwhelming. So don't worry, I'll be there. I'll help guide you, and then we'll get acclimated to kind of my exam style. And then once you've done it once, you'll ace the next one. So everyone's going to be fine in this course and do extremely well. Chi-squareds, z-table, then there's probably going to be some type of hypothesis testing. So with t-tables, z-tables, again, there's lots of things I could kind of throw in there. So that's exam one. So I think, again, generally in terms of conceptual topics, people do really, really well in this exam. The only issue is if you haven't taken a course with me before, there is a time component to my exams. I ask a lot of kind of questions within these 4 questions. So make sure, again, you simulate exam conditions when you are doing your practice exam. So that's exam 1. Exam 2 is a little bit more straightforward of a structure. But again, the conceptual topics, Fourier is a little bit difficult, especially if it's the first time you're seeing it. Even honestly, the second time you're seeing it, it takes a while to appreciate the beauty of it. But Fourier analysis is unmistakably or undeniably beautiful and powerful. So 4 questions again. Most certainly, I'm going to ask a CFT question, continuous Fourier transform. I'm going to ask a discrete Fourier transform question. And then there's going to be some problems with design of apparatuses and design of experiments where we deal with these concepts of signal aliasing and spectral leakage. So, sounds pretty straightforward. I've taught this course a fair number of times now since 2018. It always still seems to give people issues, but again, as long as you kind of attack it, we're going to do even better on this exam. People have continued to increase their scores on average on this exam, so I'm hoping that I think we could really knock this one out of the park this semester. So, in the last exam, the mechanics exam, that is my exam that is most fun for me to teach because I love materials science and I love mechanics. I've learned to love mechanics. I used to actually did not like it as an undergrad, but I really, really appreciate it. Again, when you have time to teach it, you can really appreciate the beauty of mechanics. It's a little bit more stressful when you're taking it for an exam. But anyways, so for the last exam, there's lots of kind of combinations that I could throw out here and deal with. So there's almost definitely going to be some type of Wheatstone bridge. Actually, there's probably going to be 2 of these problems with kind of different configurations, whether it's like a calibration, like a shunt, or just like a configuration of how many arms are in a strain gauge and measuring some complex, stress state, and then figuring out either strain or stresses using kind of this tensor notation again as well. So this is good for at least 1, 2 to 3, 4, 3 questions. Another way that I could kind of throw or ask kind of some questions around here is you could change the alignment of strain gauges to measure certain properties. So I call this question strain gauge orientation. So you could change essentially either the location or the orientation. So you could lie like the strain gauge like this long sample. You could flip it. Actually, that's not bad. So strain gauges typically have these wires here. So you could flip it, and you could change whether you're measuring bending or measuring tension or lots of different kind of things. So this exam, I get really creative, but you'll see that it comes down to really, really basic mechanics and materials equations, and we're going to have a very, very robust procedure and algorithm for how to attack every one of these problems. So don't worry about this. This is the most fun part of the class, at least for me. Hopefully it is for you as well, and you'll learn some really fun material science related topics as well. in addition to part 1 and part 2 is also helpful. So that's kind of what the class is we have in store for this semester. It's going to be really fun. Again, if you have any issues, please come to me early, and we can kind of figure out a way to match kind of our expectations and our understanding of the lecture material and see what we can do. But yeah, I'm looking forward to a fun semester. So in the next video, we're actually going to get into lecture 1 material, and we're going to talk about measurements. How do we basically make measurements, definitions, standards, why are measurements important, some uncertainty, and then 2 types of measurements, 2 broad categories of measurements. 1, direct measurement, and then 2, a more common, or direct measurements are more easy to do. Indirect measurements are actually more common, but a little bit more complex, again, because we need to kind of measure these like really small quantities where we need to have extremely high precision, because we are starting to really measure some really unique quantities. The LIGO, gravitational waves, come to mind actually to me. So more, it's not just good enough where we can't have an error of, or an uncertainty of a plus or minus even a milligram. We need to have, nanomolar resolution. So we'll deal with all that next time. So yeah, thanks. Please keep watching the videos, and I'll see you. Bye.